This is Berlin, the latest module in the Leibniz Binary Subsystem from Xaoc Devices. On the surface, it's a pretty straightforward compact oscillator with FM, hard sync, and square and saw outputs. But round the back are connectors that let you run the 8-bit data that creates the saw wave through other modules in the Leibniz Binary Subsystem. And that's where the fun really starts. You can pair it with Jena to create a vintage-style wavetable oscillator. And you can use Jena's through-zero phase modulation input to create 80s FM-style tones. It can drive Jena at sub-audio rates too, giving you a huge range of complex LFO shapes and gate patterns. And Berlin gives you a quick and easy way to drive the special drum pattern banks in Jena. You can creatively mangle the 8-bit data by cross-patching bit streams. Or you can get a bit more abstract and noisy using Rostock to loop and scramble portions of the wave cycle. And there's a high-frequency Leibniz clock output that you can run through a frequency divider to build a unique-sounding subharmonic oscillator. Now, I don't want to get too bogged down with an in-depth explanation of the Leibniz Binary Subsystem in this video, partly because I've covered it fairly extensively in a couple of previous videos on Erfurt and Rostock, which you can check out via the links below, and partly because I don't think you actually need to understand too much about it to start having fun with Berlin. In fact, I'd go as far as to say that if you've been curious about Leibniz in the past but maybe found it a bit hard to get your head around, I really think this module is the one that might make it click for you. It's definitely an easy way in. But in a nutshell, for anyone new to it, the Leibniz system is a set of modules that Xaoc Devices have designed to work together, which can send and receive digital signals in 8-bit binary format through special ribbon cables that connect on their rear panels. These signals could be standard audio or CV signals that have been converted from analog to digital using the 8-bit ADC in Dresno, or data generated from scratch by a module like Erfurt or Berlin. The data can be processed in various ways and converted back to analog via the 8-bit DACs in Dresno and Berlin, or because the data is transmitted in the form of 8 individual streams of constantly changing bits, and several of the Leibniz modules give you access to these in the form of gate outputs on the front panel, you can use the data to trigger drums or modulate other things in your system. It's so open-ended that it can feel pretty daunting, but I think the key to getting your head around Leibniz is to focus on one simple application at a time. You don't need to connect everything to everything. And that's where Berlin comes in. It's a great, simple starting point for a Leibniz system that's ideal to pair with one or two other modules. The most obvious partner is Jena, and I think that pairing is probably the way to get the most instant gratification. But it also plays nicely with Rostock. So I'm going to run through Berlin's controls and explain how it works, then I'll get some patches going to show what it can do. Berlin's front panel is pretty simple, and most of the controls and connections should be familiar to anyone who's used a standard VCO. It's 8 HP wide, and at the top left we have a volt per octave pitch CV input. Next to that is an exponential FM input with an attenuator, and at the top right is a hard sync input which restarts the oscillator's cycle. In the middle is a big fine-tuning knob, and below that is a pair of buttons for selecting an octave range. There's a CV input for this too, which lets you move through the octaves using 1 volt increments. At the bottom left is a square wave output, and in the middle is an output which is either a clean saw wave or a version of that saw that's been processed by whatever modules you've connected to the Leibniz bus via the rear panel. This Leibniz signal path can be engaged or bypassed using the LBZ link button and gate input, which effectively let you switch between a clean and processed saw. Switching this at audio rates can be quite fun, as you'll see later. Finally, at the bottom right is the Leibniz clock output, which is basically a square wave that's running at a much higher frequency than the square and saw outputs. And this is probably a good point to explain what's actually happening inside Berlin. You see, the oscillator core runs at a very high frequency, 8 octaves higher than the frequency of the audio output, in fact. The saw wave is generated by this high-frequency oscillator driving a binary counter which counts up from 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1, 1. In other words, all 256 values that are possible using 8 binary bits. This produces a 256-step upwards ramp which is converted to an analog waveform that spans -5 to +5 volts using the built-in DAC. The square wave output is derived from the most significant bit, the leftmost bit of this 8-bit number, which is high for the entire second half of the cycle, once the counter reaches the 128th value, basically, so you always get a perfectly square wave with a 50% duty cycle. One thing to note is that the saw wave always includes all 256 values. The frequency of the clock itself that drives the ramp generator varies throughout the tuning range, so there's never any audible aliasing. It's the same way classic digital synths like the Fairlight CMI and the PPG Wave worked, and it means you get a rich, full waveform right through the whole frequency range. It's also worth mentioning that the DAC that delivers the analog output is asynchronous. In other words, unlike the one in Dresno, it's not driven by a clock, but simply updates its output voltage whenever the digital signal changes. Anyway, that's definitely enough theory for now. Let's get it into the case and start making some noises. Okay, let's get started with what's probably the most straightforward pairing for Berlin, and that's Jena. Jena's been around for a little while. It's another module in the Leibniz Binary Subsystem, and it's basically a big bank of wave shapes or transfer functions that take incoming binary data and spit out a different set of data. What that really means in practice is you can feed in a rising saw wave like the one from Berlin in binary form, and what you'll get out of it is different wave shapes. It lets you use it as a kind of vintage wavetable oscillator, which is what I'm going to do in this patch. So what I've got set up behind the panel is the Leibniz output of Berlin going to the Leibniz input of Jena, and the Leibniz output of Jena is going back to the Leibniz input of Berlin. So it's in the kind of loop behind the panel. It's actually also running through Potsdam and Rostock, but they're not doing anything in this patch. So for all intents and purposes, Jena is the only thing acting on that Leibniz data saw wave. At the moment, I haven't got that engaged. I've just got the saw output being generated by Berlin on its own. That's going into the scope and then into Tallinn VCA. I've got a little sequence set up on Moskwa, just a really simple sequence of notes. I've got an envelope from Xaoc, which is going to drive the VCA. And that's kind of it. Let's have a quick listen to the raw saw wave on its own. So just a nice, clean, straightforward saw. I'm not filtering this at all. But if I engage this Leibniz switch, this saw will be routed through Jena and transformed into something else. So this is bank 0. And if I start to rotate the shape, you can hear it starting to move through various different waveforms. They're all quite smoothly connected one to the other. So if you modulate this with CV, which I can do, for example, by patching in an LFO from Batumi, which I'm going to attenuate in Samara and run that into the shape CV input. That's now scanning through all those shapes. And if I go to the other banks, each bank has got a slightly different flavour. Add a little bit of delay here as well. So you can hear there's a pretty huge palette of wavetables. Not doing anything clever here really, I'm just scanning through them with an LFO as it's playing the sequence. You get the idea, they're all slightly differently flavoured. Let's go to bank A, which I know is quite a nice one. Let's take the LFO off. And let's try modulating it on a per note basis with an envelope from channel B of Xaoc. So that's getting a bit of articulation on each note. Let's Try reversing that wave. Let's just try adjusting the start point. And of course, if you've got more interesting shapes to modulate this with, which luckily Xaoc is full of interesting shapes. So there you go, wavetable oscillator. Not doing anything too clever with the modulation here, but hopefully gives you a little idea of the kind of palette that Jena can offer. So sticking with the Berlin and Jena combination, I want to try one more feature of Jena, which is its through-zero phase modulation input. This opens up a whole world of kind of 80s style DX phase modulation sounds, which are really great for techno. I'm in bank 7, and shape 0 in bank 7 is a pure sine wave. I'm going to modulate it with a sine, or the fundamental output from Sophia, which is Chaos's analog oscillator. I'm going to drive both Berlin and Sophia from the same pitch sequence coming from Moscow. I'm going to run the output of Jena straight through Tallinn. Again, no filtering in this patch. And let's just get a little sequence going. Got a little kick drum from Squid Sample as well. So that's the pure sine wave. And I've got the output of Sophia routed through Samara, so I can control the amount of that going into the phase modulation input. So we can get these nice kind of clanking phase modulation tones quite easily. Play with the tuning in Sophia. We can get slightly more harmonic sounds. These kind of quite low-pitched, clanky sounds. Now, channel 2 on Samara is also the Sophia output, but this time I've routed it through a VCA and the palette case, and I'm opening that VCA with some step random from PAMS. So this makes for a much more dynamic kind of sound where the depth of that phase modulation is being randomly adjusted per step. That same step random is also modulating subtly the decay time, or the total length of that envelope in Xaoc that's opening the VCA. So instant techno. I've got the other two channels on Samara. I've got a fixed offset from channel 3, which is routed to the shape input on Jena. So this lets me, if I turn off that phase modulation for a sec, this lets me manually scan through those waves rather than turning the encoder. And the fourth channel is also routed or mixed through to the shape input, but this is a slow triangle LFO unipolar from PAMS, which basically scans, you can see on the digits there, it'll go from 0 up. And depending on how high I set the attenuator, that'll set the upper limit. So I can kind of morph that sine wave by changing the shape in Jena, and at the same time I can add this phase modulation. So I'm just going to jam on this with some other drums for a minute. So in this patch I'm still using Jena to process the saw from Berlin, but this time I've got Berlin tuned down to LFO mode, or low frequency range. I've picked a wave shape in Jena, which is on the scope here. It's a nice kind of wiggly shape to give me a kind of complex LFO. And I'm going to use that to modulate some parameters in Sophia, and we'll just listen to this as a kind of complex drone. The way my Leibniz bus is set up, I've actually got the output of Berlin going into Jena, going into one input on Potsdam, which is like a switcher for the Leibniz bus. Potsdam's got two outputs. One of them is running through Rostock and back into Berlin. So Rostock is it's a delay pipeline for the Leibniz data. I've done a previous video on that, and I'm going to come onto that in the next patch a bit more as well. But for now, all you need to know is it's going to delay the signal slightly by 64 steps, or about a quarter of the duration of the wave. And then I've actually also got the second output from Potsdam that's running into the DAC side of Dresno. I'm clocking that from the Leibniz clock in Berlin, so I'm going to get the same wave but 64 steps, or 1/4 of a wave out of phase. I'm going to use these two complex waves, which I'm getting from the DAC in Dresno and the DAC in Berlin. They're going to go into the two ratio inputs on Sophia for the two sides of the oscillator. And yeah, if I start bringing some of these things up, I'm also taking bits 6 and 7, which you can see in Jena here. They're kind of turning on and off intermittently as this wave changes. They kind of come on as the wave hits its peak. Running them through a bit of attenuation in Samara, and they're going in to the warp inputs on Sophia. And as I just play with these parameters too, and I've got a couple of other unsynced ramping LFOs from Batumi going into the damping. So I've got damping, ratio and warp, which all affect the ripple elements on Sophia. And I've got the two sides basically being modulated similarly but independently, with unsynced LFOs there, occasional gates from Jena, and these two in phase, out of phase but related complex shapes. I'll bring up the starting points. Got the whole thing running through a bit of big reverb as well. But if you've got an oscillator or a voice that can take a lot of modulation, it's quite fun to take stuff like this, and if we just change this, we can just go through this wavetable. And there's thousands of these shapes in Jena. So there's one more thing I want to show you about this combination of Berlin and Jena, and that's the special drum pattern banks in Bank E of Jena. Now these are different from the other banks in that they are designed to give you gate outputs at rhythmic intervals to produce drum patterns. You get a set of 8, and you can see them flashing there. You basically put Berlin into low mode and set the tempo with the big knob, and that's kind of it. Let me just fade this up. The way they're kind of laid out is at the top of the set of bit outputs, which is bit 7, that's a kick drum, snare, 2 hi-hats, bits of percussion and a cymbal at the end. Fairly standard kind of drum layout. I've just loaded one of the kits in the Squid sample from the factory USB, and it's kind of sounding like a drum pattern, which is great. And then there's 256 of these, and they're all kind of subtle evolving variations, so as we just go through the patterns, this set here get more and more complex. Of course you don't have to use these for drums, you can use these to trigger anything else you like in the patch, but it's quite easy to demonstrate them with a drum kit. one question you might be asking is how do you sync this to the rest of your patch? And there's really two ways. The easiest way, to be honest, is to use Berlin as the master clock. And what I've done here is I've just taken that Leibniz clock out. I'm running that into Erfurt, operating as a clock divider. It's not connected on the Leibniz bus, just running independently. And this will give me various clock divisions of the very high frequency clock. So if I want a 16th note, say, it'll be on bit output 3, I think. The other way, if you want to use an external master clock, is a bit fiddlier. And it basically involves beat matching it, effectively as if you're a DJ, and using the hard sync input to reset it every 2 bars. These patterns, by the way, are 2 bars long, as you probably noticed, or 32 steps. Now I'm just going to scroll up a little bit to one of these 4/4 ones, and let's just load in an 808 kit, say. So they're pretty usable patterns. Not totally sure how I'd use these in the context of a track yet, but it's a nice little extra in Jena. So although Jena is obviously a really powerful pairing for Berlin, there's also quite a lot you can do with other modules in the Leibniz system as well. So as I explained earlier, I've got the Leibniz configuration in this case set up so that Berlin is going out through Jena into Potsdam, and from there it's going through Rostock and back into the DAC in Berlin. So I can bypass Jena by turning off its link button, letting that be unselected, and then I'm feeding the saw wave through Potsdam and through Rostock. Rostock's not really doing anything at the moment other than delaying it by 64 clock cycles, or a quarter of that 256 wave. But let's just have a listen to what happens if we cross-patch some of the bits through Potsdam. I've got the kind of incoming bits here and the outgoing bits there. At the moment they're linked with this blue link button, so the data will just pass straight through, but we can interrupt that with manual patch cables. So here's that saw wave. And if I take bit 7, say, and go into bit 6, you can see how the shape and sound changes. Let's go from 6 to 5. Let's go from 5 to 7. So you can see just by playing with these, you can develop some interesting Let's try filtering that down slightly, running a little sequence. And I can fade in the square wave from Berlin as well. I've got that running into this Samara mixer before the filter. So because the frequency effect of this bit swapping has kind of raised the frequency an octave or 2, this square's now acting like a sub. Which gives us quite interesting textures. And of course, if you have switches and other modules, you can get some clever routing and stuff going on to kind of repatch these in real time. So that's what you can do with Potsdam. Let's have a look what you can do with Rostock, because that's where things get quite interesting too. So Rostock is a data pipeline or a shift register which basically delays the Leibniz data coming into it by however many steps you set with this length from 1 to 64. In fact, if you look at the scope, I've got the square from Berlin underneath the saw, and if I adjust the length of this pipeline, you'll see that saw start to move to the left. It's kind of moving its phase effectively relative to the square. You could exploit that by kind of mixing the two together, and you could modulate that pipeline length and get a kind of PWM kind of effect by moving that saw around. But what I'm more interested in is using the loop and scramble functions in Rostock, which will take that data pipeline and stop new data entering it, or with scramble engaged, it will use logical XOR to reorder those bits. It's easier to let you hear it than it is to explain it. Let's just get that sequence going again. And let's turn the filter back to fully open. And if I hit loop, and depending on which particular part of the cycle I happen to catch, I get a signal that's basically 4 octaves higher because it's a quarter of the wavelength. Not that exciting, but let's hit scramble. And let's clear the buffer manually. And I get a new randomly generated kind of wave. So depending at what precise moment I hit that clear button. So why don't we hit that clear button with the same gate that we're using to trigger the envelope. Which is giving us a fresh waveform on every note, basically, which is quite cool. Now, at the moment the buffer is 64 notes long, 64 steps long rather. Listen to what happens if I decrease it to an odd number. This is where we get into these crazy digital noise kind of tones that the Leibniz system is brilliant for. So we've got a kind of tuned noise oscillator now. If we want to bring a bit of tonality to this, another thing we can do is switch the Leibniz wave back to the saw wave for half of the cycle. If I use that square wave to control the Leibniz link switch within Berlin, so I'm self-patching a copy of that square. Now half the wave is that saw. If I press the button I can choose which half. Whether it's starting with it connected or disconnected. And certain values of length of pipeline produce more or less harmonious results, and when I get down to a factor of 256, like 32 say, we're back in harmonic territory again. And I'm generating a new wave with every note by hitting the clear buffer. So this really is, although Jena's got these banks of preset waveforms, Rostock's kind of like this infinite random wave generator. Let's filter this down again. Play quite nice like this, but as soon as you get to these other values of pipeline in Rostock, we're back in this kind of noisy territory. I quite like these kind of little noisy bites that it gives the wave. And reinforce it some more by mixing in that square back into the audio path. Okay, for this last patch, I want to explore using the high-frequency Leibniz clock output of Berlin to drive a frequency divider, which will give me octave subharmonics, square waves derived from that clock. I'm going to use Erfurt from Xaoc Devices as the frequency divider. I'm not going to go into a huge amount of detail about it. I've done a previous video on Erfurt and Lipsk. All you really need to know for this patch is it's going to operate as a straightforward clock divider working in octaves, so that the bit output 7, the highest one here on the panel, that's going to produce an output that's 8 octaves lower than the input. And as we go down the panel, we're going to go up the octaves. I'm mixing 4 of those together through Samara, through the scope, through Belgrade to filter, which is wide open at the moment. And yeah, let's just have a listen to that first lowest octave square wave. So that's effectively 8 octaves below the Leibniz clock, so it's pretty much the same as the square output of Berlin itself. I've got the next octave up going into the second input of Samara, but I'm going to the inverting input. So as I turn this up, it will actually subtract from that square wave. And likewise, the octave up again on input 3, I'm also subtracting. This lets me design a kind of stepped, very crude downward saw wave, effectively like a staircase. And input 4 is an octave up again. This time it's going into the positive input. So you can see just by kind of playing with the balance of these 4 octaves, we can generate some quite interesting wave shapes, which we can then filter, which sounds quite cool. So the other thing I thought I would try is modulating these buttons on Lipsk, or the gate inputs on Lipsk, which will change the count increment of Urfa, and that's going to produce something that's not straightforward octaves, but something a little bit more interesting, because these gate patterns are no longer going to be completely uniform. They're going to be turning on and off at different intervals, producing different frequencies. It always sounds quite musically interesting. They always sound like harmonics in some kind, but they're slightly odd. So let's have a quick listen again to just the low octave, and if I manually toggle a few of these buttons, they're all kind of related to the harmonic series, but different combinations produce some quite different tones. So I thought, let's use Batumi in phase mode and take 4 rectangular outputs or square outputs at the same frequency but at different phases, and let's modulate 4 of these inputs. Let's just go into one. I'm just going to go down a couple of octaves on Berlin. So we've kind of got a strange sort of sequence going on here. Let's give it a bit of reverb. And let's filter it down a bit. And I'm going to take the sine LFO from the first channel of Batumi. I'm going to go into the filter FM input as well. Belgrade's such an unusual filter, it sounds brilliant on a patch like this. Let's just turn up the resonance too. So this is just the low octave square wave. Let's bring in some of those others again. If we play with the phases of the LFOs that are controlling Lipsk, we can generate these new patterns, which do repeat but are quite hard to predict. So I'm going to leave it there. This has been quite a long video, so congratulations if you made it this far. Hopefully you've got some idea now of what Berlin can do in conjunction with some of the other Leibniz modules. I'm really just scratching the surface here, and I'm looking forward to exploring some even deeper patches in future. If you've enjoyed the video, please leave a like and a comment, and consider subscribing to the channel if you haven't already. Thanks for watching, and I'll see you next time.